I'm very, very happy to introduce our speaker today. So I know Pedram from way back. He was actually one of my very first physics instructors in undergrad. So he was the lab TA for my 2 freshman labs. And so we rolled cars down hills and dropped BB pellets down tubes of oil together. And so he did his PhD at Princeton with Ali Yazdani doing STM and hardcore condensed matter work before moving on to Santa Barbara to work with John Martinez on superconducting circuits. And he's now one of the key players in Google's quantum computing effort with superconducting circuits that sort of grew out of the Martinez group. And he's going to tell us all about the amazing experiments that they are doing with these systems. And so with that, Pedram, take it away.
Thank you, Alicia. Yes, indeed, I don't see any faces or anything, so just interrupt me. It would be good to make it an interactive conversation. Yes, thanks for the opportunity. Thanks for everybody's time to be willing to listening to this talk. I'm a member of the Google Quantum AI team, and this is one of our last pictures before COVID. It's a large team, I think probably maybe twice this size now. And we are, our mission is to make a quantum computer. Our daily life is to advance quantum technologies, and we celebrate or we benchmark our advancement by certain milestones to communicate with the broader community on where we are in this milestone. In particular, recently, maybe 2 years ago, we wrote a manuscript which shows how what our capabilities are at that moment. The work appeared in the work is at that moment was called quantum supremacy, but to be more politically correct, I would refer to it as beyond classical experiment. And data of it is also available, so you can also examine it yourself if you want to. But let me tell you what this work means and what went to this work, and then from there I try to connect it to our current plan, and then I leave it to you about our future destinations. Because maybe several years ago, when I used to give talks, I used to very emphasize about roadmap and philosophy and what we are doing and what it should mean, and try to explain in that sense. But now I feel like just for a group of physicists, this also could happen. For a group of physicists, explaining what experiments we do should be sufficient to guide them to understand where we are going, and I can leave the judgment to them. So let me tell you the beyond classical experiment in a very brief way, and then you see what's happening. Oh, by the way, do you see my mouse? That's a key question.
Yeah, we can see that.
Okay, good. So here is a group of qubits, a couple of them highlighted, and you apply a sequences of pulses on them, randomly chosen, but you know which set you're choosing. So qubits are starting from a very known state, let's say 0, 0, 0, and then at the end of all these, you measure all the qubits, you get a bit string. And then you start competing with classical computer to predicting which bit string should have come out. The key in the experiment is that first we talk about the fidelity of the gates, and then how well we can implement these gates. And it turned out only when the fidelity of the operations are high, you can outperform a classical computer. All the works that came later try to outperform or say that this result could have been duplicated in much shorter time, and so usually either they find something very strange in the logic, they do something very unreasonable, they just work with a single bit string or something very strange, or they forget about this factor of fidelity. If we did not have the fidelity which we communicated in the main article, summarized in here, if we didn't have that, the experiment wouldn't have been that difficult to perform. At the limit of very low fidelity, tossing of a coin would have been as good as performing the experiment. So in the experiment, in the manuscript, we talk about how still we have predictable power if we can simply switch the order of the gates, while the classical computer just fails to produce those bit strings, and in that sense, we perform the classical computer. So it's interesting, you create certain sets of bit strings, and is known to be a hard problem, according to the proof by Vazirani, I think. But then the problem is this doesn't have a broad community of interest. There is no big community that would show interest in this problem. Is contrived, is precisely defined problem, is well-defined problem, but it's highly contrived in a sense that who cares about this problem? So here I'm making a very crude, very back of the envelope plot based on the discussions that we had among a couple of groups and a couple of people, nothing to be taken too seriously about it, but it roughly says why the beyond classical experiment was the first experiment that we could have done, because it's the lowest in the number of qubits and and in terms of gates fidelity that one can hope for and still get something out of it. So now we are trying to do something that the physics community, chemistry community, someone bigger group of people care about the experiment. And the problems either need more number of qubits or much better gate fidelity. That is what NISQ is all about. NISQ, on the other hand, of course, you can make a fault-tolerant quantum computer, which is totally off the chart in this case. You have to go really far down the road to make it to happen. So note that the challenge is not to make more qubits. The number of qubits scales linearly. So if you have twice more qubits, you can do good physics or chemistry non-equilibrium dynamic problems, but you have to have order of magnitude in fidelity. The vertical axis is logarithmic. And the chemistry problems are twice in size because there is this Jordan-Wigner transformation. The electronic fermion problems don't map easily to platforms which are bosonic modes of oscillation based physics. So that's why chemistry is just twice in size. And I don't remember what exactly we meant by fermionic simulation versus quantum chemistry. As I said, these plots are super rough, but they are more or less correct. I think you can get the interest of community if you have gates that are orders of magnitude better, but you have about twice more qubits. So this is where NISQ should be going, I think. And in this talk, I present two experiments which tells you where we are and what we can do now, and I leave the extrapolation to you. But just to be complete, it would be strange if I don't even say a single word about our platform. Let me introduce the platform and what it does. I don't know how familiar it is to people these days, but the whole started with the work of Brian Josephson, who figured out if you have two superconducting islands very close to each other, such that Cooper pairs can coherently tunnel from one side to another, and if there is a phase difference between these two islands, the Ginzburg-Landau superconducting phase is different between them, it would lead to a DC current between the two superconducting islands. And if this phase difference between them, here phi is the difference between phi1 and phi2, if this phase is have some time dependence, you can get a voltage across the superconducting island. And this is how in the lab these days we make these superconducting islands. They are separated by about 5 nanometer of aluminum oxide. And here, how this idea evolved to form into a qubit. It turned out that this is a Josephson junction can be used as a nonlinear inductant. And if you shunt it with a capacitor, you can get a cosine, you can get an oscillator with the profile of with the potential of the oscillation being a cosine profile versus an harmonic oscillator, which has a parabolic potential. And this is a huge difference in a sense that now the level spacing would be non-uniform. And this non-uniform give it some atomic feature, atomic-like behavior, meaning now you can address levels individually. The difference between 0 and 1 is more than the difference between 1 and 2. And that's sufficient to be, now you can address transition between levels individually. And this is how transmon qubits at the end of the day look like. The whole bulk of it that you see is a capacitor, and here is this Josephson junction, two Josephson junctions, so you can have control over the frequency of where the resonance is going to happen. And this is how, when we put it together, this is not exactly Sycamore device. This is not the picture of the Sycamore device, but some device similar to that, few years old. The basic ingredients of physics are there. So the cross-shaped capacitance I showed you, there is nothing particular demanding it to be cross-shaped, so we made it to a straight line. This is this segment of aluminum, which we colored in red, is a capacitor. The inductor is in here. The Josephson junction is here. It's hard to see with eyes. And this shape is another capacitor, which is mainly an inductive capacitor in this case. Sorry, Q is a qubit. Is dominant by its inductance in this case, and is provide the coupling between the two qubits. You can see lots of lines, lots of signal lines coming from below. They are used to control the states of the qubits. One is an antenna to drive the qubit. One uses the frequency of the qubit, and these lines are controlling the coupling state. We are able to turn off the coupling between the qubits completely, or in the order of nanosecond, make it to maximal coupled states that we like. On top, you see lambda over 4 resonators. These are linear resonators, which the shift in the frequency by a few megahertz tells you that if qubit is occupied or not. And there would be 2 lines to read the state of all these 9 qubits simultaneously. So in each run, you get a bunch of complex numbers, which you can very quickly interpret them as which qubit is in state 0, which qubit is in 9. So in one shot, you can read the states of all the qubits. And every output of experiment essentially would be a 9-digit, in this case, a bit string of 9 digits. If you're bored from this detail of if you're a theorist or for one reason or another, you can think about the system as the governing dynamic of the system is a Bose-Hubbard Hamiltonian in the absence of drive. So you would be in one of the photon conserving manifolds. There is a coupling which gives you this hopping term. There would be individual frequency of the qubits, give you this term, and then nonlinearity translates into this term, the Hubbard U of the interactions. So this is what the device is, and with that, I want to get to the first experiment. Okay, so the first experiment is the beautiful experiment of time crystals. Has grabbed much attention of the media recently, and I get back to why media is paying attention to this. But let me tell you my narrative of the story of what happens. So crystals or breaking spatial periodicity, breaking spatial symmetry, sorry, is attractive and is interesting, and we can think about lots of examples that it happens in nature around us. The liquid crystals, ferromagnetism, all the beautiful crystals that we see around ourselves. Another very interesting periodic pattern in time, they are also fascinating and they are also exciting to us, such as solar system or driven oscillators or something. But there is a difference as you start to list these beautiful or charming or very canonical examples that you see around yourself. As you start to list them, you realize a difference. You have to really think hard to figure out examples of temporal ordering, periodicity in time, that are more than single body, that are many body systems. It turned out that when you are having temporal ordering, very commonly, they are unstable. Meaning that when you have a crystal and you you perturb it somehow, very soon it can come back to its full periodic shape. When you have temporal ordering in a many body system, it's usually unstable. If you come back and take a look at it, or if you perturb it, it's not going to be there. And if you can think yourself of an example of many body system which shows temporal ordering and is stable, it's driven and more entropy is generated and it's open system and entropy is dumped somewhere else. Finding a many body system that oscillates indefinitely in isolation is really hard. And this is the core, this is the definition of the time crystal, and this is the core of the difficulty of time crystals. So this is a very precise definition, and since it's very challenging to realize such a many body system that in isolation oscillates forever, indefinitely, according to theorists, that is beautiful and is hard to realize. Well, why is that the case? Because there is a challenge and there is something impossible. So let me explain the challenge first, and then I say what is impossible about it. And that's what is really hard. We want something that is a many-body system, and 2 lines signifies isolation, that's isolated between 2 configurations indefinitely. I love this indefinitely that theorists demand us to prove. Second law of thermodynamics is not here to help. It says that entropy of a closed system cannot decrease. It doesn't say it has to increase, it just says it cannot decrease in time. So if you generate more entropy, there's no way for it to go, it got to stay, and it's just going to get worse and worse. So you just have to live with it, that it's really hard to avoid this. It's just really hard. It's not impossible according to second law. It's just really hard, and most likely, most scenarios is that the systems reach some maximum entropy states, and which the system would be some in the superposition of all possible configurations, and it doesn't take any order. So this is really challenging. This is also impossible. So let's try to synthesize a system which could show periodic oscillation. We know periodic or perpetual motion in quantum mechanics is feasible. You get a superconducting ring and you pass some current through it, and it's just going to persistently move. But this doesn't break time translational symmetry because the motion is uniform. It doesn't allow you to distinguish instants of time. There is no difference between instants of time since the motion is very uniform. In 2012, Frank Wilczek proposed that if we introduced some interaction, some level of, attraction between the Cooper pairs that goes around this loop, they could bunch up together, make a soliton kind of collective of particles, and then when they move around, you can see that there is an oscillatory motion, because now you can, based on the motion of these lumps of particles, you can tag instance of time, so you can break time translation of symmetry. A few years later, Watanabe and Ashikawa sat down and wrote down a very precise definition that this system could have. They say, well, what do we mean here? What are we asking here? They say, well, how about having a two-point correlation function in time and space, two distinct points in time and space? And technically, we are asking for this two-point correlation function to show some non-trivial behavior. And they demanded this to be time-dependent behavior. And they show when the system is in equilibrium and you consider the Gibbs ensemble of the system, then it's impossible for this two-point correlation function to show time-dependent behavior. It has to be time-independent. So therefore, having, according to them, having an equilibrium, having time crystal, or having perpetual oscillation in equilibrium system, in systems in equilibrium, where there is no exchange of energy or net new entropy is generated, is impossible. So let's speak that in terms of the spectrum. In the spectrum language, we say, well, you know, like our ferromagnets, we are looking for something that is ground state, was showing some sort of ordering, and the entire spectrum can do anything it like. But now we show that this in equilibrium is impossible. So we got to move away from equilibrium. The simplest thing that could come to mind is that we drive the system, we periodically drive the system. These seems to be very natural cousins of equilibrium systems, because you can look at them stroboscopically, and it more or less could look like equilibrium. At first sight, this doesn't buy you anything. If you drive the system now, instead of talking about spectrum energy going this way, you don't have ground state anymore, and then you got to talk about the unitary of the system, and the eigenvalues of the unitary are e to the I theta, where theta is the energy. So these are the values of the eigenenergies of the system, and they would be would be on a unit sphere, because eigen states of the system are all the shape of e to the I theta. But there's no ordering a priori given to you. It's just going to be now a bunch of states on a circle. However, the very interesting physics of many-body localization comes to help. Many-body localization systems are systems that are they don't absorb energy from their drive, and entropy growth in them are saturated. And now, if you combine these two physics together, you have a periodic drive, and you introduce disorder in the system, then you can have a chance to satisfy all these criteria at once, and you can have a system that is that does not generate new entropy in the system and doesn't absorb energy, and there is and you can see it. So here is the talking about the same physics slightly pictorially. So in typical scenarios, as I mentioned, commonly the entropy of the system goes to the level that maximum allowed entropy of the system, all possible configurations. MBL leads to very slow logarithmic growth of entanglement, and at the end, I think a very, very long time, it would not saturate to the max value, but to a smaller value. Essentially tells you that when you disorder the system, when you are driving it, the energy absorption would be capped, would be bounded, and it would not grow unbounded, in contrast to periodic drive, which energy just keeps constantly absorbed from the drive. And this is the scenario that we are trying to establish. Let's see if I have that. Note that the many-body localization is really at the core of the physics. We really have to establish many-body localization. So now I have written a longer definition of what time crystal is. It's the same definition as the one I said before, indefinite oscillation in isolation. That's all we are after. But now I'm spelling out into several criteria that we have to prove in our system to show we have established a phase of matter. We are really trying to make it distinct from a response. There is something that you show a response. There is another business is to show that you have established a phase of matter. Let me explain how far we have gone into this business. First, you want to show that the response you are seeing is a stable over change of parameters, and also the phase we're after has to be many-body localized. Second, we have to show that is not thermalizing and is not slowly decaying, is the criteria of indefinite oscillation. So we have to make our best attempt at showing indefinite oscillation. As I said, the many-body localized is an eigenestate, well, maybe I didn't say, is an eigenstate order phase, meaning that all eigenstates of the problem have these many-body localized features. It's a transition in the eigenstate of the problem. So we have to show all eigenstates of the problem are showing this behavior and are obeying the order. Another thing is we have to take it to infinite limit system sizes. So we have to make our best effort at that too, which we do it with finite size scaling. So you can follow these color coding in here to see which each slide is correspond to. But let me get started. This is the unitary that we construct, the unitary and then we repeat it in time. This unitary composed of three parts. One is individual Rabi drive of qubits. You rotate each qubit. And this is the coupling term, which make the qubits to talk to each other.
Sorry,
they couple to each other. It's a ZZ coupling term. And at the end, we introduce some disorder to local fields. If you don't have the last local fields, the system would be integrable. So you have to do that. But it's not sufficient to have disorder only in local fields. Again, to have proper MBL and numerical work suggests that you have to have.
Pedram, can I interrupt you for a second? This is Mohammed.
Sure.
So when you're talking about the Hamiltonian system, I understand the eigenstates and the etc. When I'm driving the system in the presence of dissipation, I have a steady state, right? So I drive.
We don't have dissipation. The claim is we don't have dissipation.
So okay, and then.
But the definition demands us not to have dissipation.
Exactly. Okay. You show that you don't have dissipation.
We provide that's the whole discussion is about. Yes, we try. Well, of course, we do have dissipation. I'm trying to argue in few slides what's my best evidence that if I remove the effect of dissipation, what we would have seen.
Mm-hmm.
The theorist, man, they say indefinite oscillation in isolation. They are very strict on the definition. And I try to extrapolate it back.
And you're going to show all the eigenstates, not just
yes,
one state that you're doing.
Yes. Good, thanks.
Can I also ask?
So, sure.
So why do you need to show this for all eigenstates?
Is the property of MBL phase. I maybe could have been clear. There was two things came with MBL. You know, that when you just look at the linear, the constant Hamiltonian MBL. MBL really is the lucky things that happens to us. Not only it limits the energy absorption and helps you to battle the second law and all that, it also tells you that the entire spectrum is many-body localized. in the theorist language is going from where ETH hold to eigenstate ordering forms. This is the spectral change, right? The entire spectrum is many-body localized.
Exactly, but I thought this was like a static property, but it seemed to me like the time crystal is a dynamical property. So why do you need to look at the eigenstates as a static property? Like, why do you need to make sure that the static property of MBL holds and not only the dynamical
if I'm
one?
claiming I'm realizing this phase, if I'm claiming I'm realizing this spectrum, then I have to show all the eigenstates of the problem are showing the property. If I'm genuinely, maybe it become clear in a second. Okay. Maybe as I try to rule out other things, it become clear. Maybe that. Okay. I have a slightly different plot that could help. So let me show you the response things first.
Could I just to clarify the question that was just asked about why the eigenstates, why all the eigenstates are important? Is there something you can point to in analogy to a spatial crystal that would be the equivalent in the definition of what constitutes a spatial crystal?
No. Can we? No, I cannot think off the top of my head. It's the other phases, the other contenders, have a mixture of red and blue in them, in their spectrum. Imagine you have a spectrum which there is a red mixed with blue. We try to prove that is not the case. Because pre-thermal phases could show a very similar responses. What I haven't drawn in here is that this red probably is not exactly fully red. It has some states in shape of blue, some of them paired also. Some of them are lighter blue, meaning that they show some oscillation for a while and they fail to show some oscillation after a while. So there are these mixed phases that I'm trying to eliminate that makes me to prove that the whole thing is eigenstate order, and this is property of every eigenstate that I start with. That's the physics.
Can you say what exactly the red and blue in these circles are?
Yeah, I think give me a second. Okay, let me present again. Okay, I got to switch, huh? Are we good again?
Yes.
Yes.
Okay, now you see more, huh? This was part of animation was missing. Okay. Every eigenstate in here can be written as a superposition of two cat states. Sorry, this is a little missing in here still. And is exactly, so every initial states we're going to make, it would be, a random bit string. And it can be, here I meant to say this is A plus, sorry, there's something missing. And that's exactly what it leads to oscillation. A plus being this guy, and A minus is the one it paired to, is every initial, well, more or less is every initial states. There is a little more into it. That's down to the tau bits of the MBL. And then after 2 cycles, you come back. So the periodic oscillation you see is the property of every eigenstates of the problem because of the fact that every initial states can be written as the superposition of each pair of them.
So the circle is one period of the driving.
No, don't think that way. This is in the energy base. This is just in energy. This is the to show energy spectrum. But I'm saying every initial state is, let's say, is 0, 1, blah, blah, is the superposition of a pair of them. The eigenspectrum are paired in the spectrum. And after you go 2 cycles, you come back. And that's what we are after to show as a property of this phase.
Okay.
Hopefully it become more clear. Okay. Okay, so let's knock them down one by one. Maybe we don't get to hear about second experiment, but that's what it is. Anyways, so let's kill the Ising coupling. Let's kill the local fields. They don't do any of these. And you do this, just turn on this G, you change this G. So now you're rabbit driving qubits. And if you rabbit drive perfectly after you go down and you go up. So this is the response. This is sigma Z of one of the qubits. I could have shown all 20 of the qubits. They would have done the same thing. And then you have a rabbit drive, which is imperfect. Now it takes more cycles to come back. You have incomplete. And you see something not that surprise. It's just you have a block sphere and you're not completing your turn in 2 cycles. So you get 2 frequency. What's the big deal? Nothing. And on the far right, you see the Fourier transform of them. You see 2 peaks, and then if you do perfect, only when you do perfect, you see 1 peak. So this is 20 independent decoupled systems. Nothing exciting in here. It just shows how good we are calibrated. Now something quite interesting is happening. I kept the first plot the same, but as I start to detune the rabbit drives, but I turn on the interaction between the qubits, it's mode locked, it's phase locked to twice of the drive, twice of the Floquet drive. So this is slightly interesting. This is showing that these systems can mode lock, and if your G, the individual qubit drive, is imperfect, you get perfect response. So it's the physics of mode locking, and it's interesting that these systems can do mode locking. But I guess anyone who attended the concert in Eastern Europe knows that people can do mode locking too when they're clapping or so. And so it's okay. So qubits can do mode locking, and mode locking in the quantum world. And this was really the emphasis of the experiments in 2017, which they show qubits oscillate very nicely. I forgot what this value is. And if you introduce disorder into the system, they all would still, they're decoupled. They all move at their own oscillation frequency. And then as soon as you introduce coupling between them, they would mode lock to a very given frequency. So they really established this subharmonic response, and then they as they change this value of G, they can really see this mode locking is stable over some range of parameters. But as I emphasize, it's all about establishing many-body localization, that you have to show this. To go from showing a stable response to forming a phase, there are a couple of more serious steps that one needs to take. So here is our version of it. You can see that when G is 0.97, and this is measured on one of the qubits, no matter which initial states we use, we see more or less the same sort of response. The response is decaying. I get to that in a second. And if you go very far away, you go to G of 0.6, you quickly decay. So what has been different between these 5 instances is that every time I start with a different initial bit string, and the choices of phi and hi is different for each case. They are randomly chosen from this set and randomly chosen from this set for hi. So this tells me, provide strong hints that there is a region that all eigenstates are ordered. Like, it's a very weak evidence at the moment. And there, as we change this control parameter, there is a value of GC that clearly we crossed, and above which it's all ordered, below which some of the eigenstates could show ordering, some of them could be paired. We don't know. I'm not going to analyze below transition in detail, but there is a clear transition at some point which is happening. Okay, so the question of isolation, which is very dear to many people's heart, let's just get to that. Here, instead of showing only Z, I'm showing 2-point correlation functions. And what we see here is that, yeah, there is a signal, but we can subtract, we can remove the effect of the coherence. And this is the technique that we use in the OTOC paper, which is Low-Schmidt echo, if the word means something to you, meaning that you construct a signal which nominally meant to be identity, meaning you evolve your system forward with lots of Floquet steps, unitaries, and then you evolve it backward in time. So nominally should have been identity, but in experiment is not. And it's the black dots that you see in here. And we just want to divide the blue curve by the black curve. And there's more physics to it. Is not as simple as just, as I said, there is something about, well, every time you do some error mitigation, some noise mitigation, you're making some assumptions, and here is the assumption happens in the depolarizing, assuming the noise is depolarizing. And then after that, you see a very stable signal when we are in the many, what I forgot to say. After I saw the distinction, I took the liberty of calling whatever is on the right side many body localized discrete time crystal, and some stuff that I don't care, I call it thermal. You can call it pre-thermal, I don't know, it's just naming. So you see very distinct case between MBL DTC and the thermal case. Even the thermal case, the signal does not survive even after normalization. But the MBL DTC provides a very steady signal up to 100 cycles we check. So this is our best evidence that how the signal would have looked like in isolation. That's the best we could come up with. And that's our evidence for it, as close as we can get. So after removing of the decoherence, that's the signal. And here on top, you can see the response across 20 qubits. It gets so periodic that it's boring and it's hard to see even what's happening in here. But there are 20 qubits that are oscillating in unison and as far as 100 cycles that we go. The normalization takes place. So let's take more steps toward establishing many-body establishing the eigenstate ordering of the phase. And what I'm trying to emphasize again is that many-body localization, which is signature is eigenstate ordering, is rather subtle. If you eliminate the disorder in phi's, phi being the coupling terms, the coupling gates are not uniform. Each takes its own phi. If you do not pick that from a uniform set, if you take it from a uniform set, the response of the system, depending on your initial state, would be very different. Here, nil, polarized, random are the nicknames essentially we give to various initial states, nil being 0, 1, 0, 1, polarized meaning all 0 or all 1, and random means it's a mixture of them. And here is the histogram of the response. You can see clearly that when the phi's are non-uniform, in fact, when you are in MBL DTC, the response is really narrow. Sigma over mu is much smaller than otherwise. And no matter which bit string you use, since all of them are eigenstates order, they are coming from a very narrow distribution. On the other hand, if you are in the, let me call it thermal phase, and if you're over there, the distribution is very wide, and things that in fact you might think that would be good candidates, such as nil and polarized, would be very much off the chart and is not showing your typical behavior of the system. The energy inset also highlights this. It's numerical work that shows that these things are very far apart. So again, I think this is now telling us that, yes, indeed, you might see some behavior, some period doubling, but you have to really establish that it's coming from eigenstate order phase. So again, now to fully establish MBL is a simplified version of out-of-time order correlations. I try to show that the fusion of particle is absent in many-body localized phase. Consider two initial states that are just different by one phase flip from each other. In the many-body localized phase, the responses of these two very close to each other, and if you walk a few qubits away, you don't feel any difference between them. On the thermal phase, the responses is very different because there is a good dynamics still going in the case. So let me summarize it in these two plots. In the many-body localized phase, when the coupling is non-uniform, you don't see any diffusion or any propagation of this disturbance, this perturbation. What is plotted here is the difference between these two responses, the difference initial conditions divided by their absolute summation. But on the thermal phase, you see there is a good amount of dynamics and it's still happening. So sure, you might find cases that are showing period doubling, but you see there's fair amount of double dynamics. This is still happening in these cases. Clearly, I'm not going to get to the other experiment, but let's just have a good conversation over this experiment. So now I want to show that eigenstate ordering is property of the entire spectrum, and we can really probe it. You know, our mentor and our hero is demanding us to check the entire spectrum, so we got to do it. The challenge, okay, so what we do, we are going to use typicality. We want to know what is the property of the ensemble, which you can pull out from a fully mixed state, but typicality allows us to use one single completely pure state and predict the behavior of the fully mixed state. How? If that pure state is completely randomly chosen from the Hilbert space, not a random bit string, but randomly chosen from the bit fully Hall random from the Hilbert space of the system. That's the theorem or assumption we are going to use. And how do you make random states? Well, you got to scramble them, but there is a challenge in here. Where as soon as you start to scramble a state, you would have a hard time reading 2-point correlation functions, because so far I was reading 2-point correlation function, but it was cheating because the z at time 0 was falling off of the expectation value because it was a product state. Now I have a fully random state. My initial state is arbitrary. I can't read this easily, and I would use an ancilla qubit, and coupling to ancilla allows me to read 2-point correlation function. So that's why the circuit is getting a little more complicated. First, you start with a bit strings, you fully randomize it, make it to be Hall random in the Hilbert space by fully scrambling it, and then this state psi s. Now we need its 2-point correlation function after we go through RUF, and that's why the circuit is slightly more complicated. Okay, what's next? What happens is that, again, you get 2-point correlation functions, as I'm saying in here, for these random states. And then you do the normalization, and you see, again, steady behavior. That's beautiful. Now, this is not for a bit string, is based on this typicality argument, is for the entire spectrum. Let me show you a full histogram. K is the scrambling, how many scrambling steps I took, how well did I do the scrambling. And you can see if I do a very good job in scrambling 20 layers of scrambling gates, you really get a very narrow distribution, which is telling you that the entire spectrum is doing one thing. So that's our, and what we are plotting here is these two numbers, what is doing at circle 30 and whatnot. Okay. Am I done? No. Okay, another demand was to go to the extreme limit of size. Of course, we cannot do that, but we can go to a smaller number of qubits. So we choose the Edward Anderson spin-glass order parameter, and we run it on to look for a spatial correlation and see if the spatial correlation are going to survive when we go larger and larger systems. And it's interesting that when you go larger and larger, when you're below the transition, the spin-glass order parameter goes smaller and smaller. When you're above the transition, as you go larger and larger system, the spin order glass parameter gets bigger and bigger. Okay, I'm want to leave 5 minutes for questions, so let me say something that's good for conclusion and move on. Okay, the work attracted lots of attention of the media, and most of them are okay, you know. But I think it's a very interesting question. Well, what they get wrong is they say Google realized a phase of matter. I think we agree that we didn't realize a phase of matter, but why we didn't realize, we disagree with them. One time you want to know, you have the Hamiltonian of the system, and you ask about ground state property, and that's what cold atom systems do. They realize the Hamiltonian, and that's when they realize it, they realize the phase, they have the phase. If we do that in our experiment, we would be realizing the ground state of both Hubbard Hamiltonian where it's coupled to environment, so it would be extremely boring thing. So when you're talking about thermodynamic phases, we have one case to study which is extremely boring. So in that, we have zero chance of studying thermodynamic phases in our system. But sometimes the question is to realize a dynamical phase. When it comes to realizing a dynamical phase, we are as good as any other system of mass spring coupled to realize a dynamical phase. The dynamical phase question is, can a system of coupled pendulums be stable without energy injection indefinitely? And our system is as good of a candidate to realize a dynamical phase as anything else. Of course, the criteria of isolation makes it extremely challenging to do it. And then because of that, because our system at the end is not isolated, so we didn't realize a phase. But the direction is really the correct direction. So the system hypothetically is capable to realize the phase. With that, I now can take questions. And we forget about the toric code experiment.
So I'll ask a rather stupid question, just to make sure that I've understood correctly what's going on here. If I've understood, what you do is you drive this many-body system with a drive that for a single-body system would be inducing Rabi oscillations.
Yes.
And you've got this many-body system where you've put some interaction between the bodies, and under the right circumstances, when you drive it a little bit off resonance, then all of the Rabi oscillations of all of the qubits lock up and are driven together, and the period doubling comes in because of the fact that you want to have a return to the initial state 2 Rabi periods rather than a single Rabi period. Have I got it right?
The period doubling is really a side product of the fact that these eigenstates come in pair. you can cook up scenarios that they could come up in triplets or anything. It's not really a important feature.
Okay.
They are just happy. It is nothing important about that. So this is, but we keep showing it because is the signature of the response, and we are arguing there is a whole world between response to establishing a phase. As you can see, yeah.
Okay, but otherwise, I basically had it right.
Yes, yeah.
Okay,
right.
now what I want to ask is, there's been a lot of people who've claimed that they've had time crystals. And one of the ways in which people have realized so-called time crystals is also a driven system. But it seems to me that that driven system is very different in the sense that the periodicity is not like having to do with a Rabi frequency, but has to do with a submultiple of the actual driving frequency, and seems to result from what I would call ordinary period doubling in a chaotic system. It looks like what you've done is very different from that. Is that fair?
The work of this Hamiltonian or this transverse fixed Ising that we turn into our unitary is the same work as Misha Looking and Chris Monroe. We're all doing the same Hamiltonian, or if you're referring to those work, we're all doing the same thing in that sense. It's just the difference comes in the choices of, more or less, we are doing the same. I don't think there are fundamental difference between these terms we choose. The difference comes in, we insist that these couplings have to be different magnitudes, different terms, than others don't. But I think there's lots of confusion on period doubling and what I really don't see any value myself in period doubling or something. There's a mode locking. Mode locking is interesting, but not anything new or fundamental for what we try to prove.
Okay, well, it seems okay. So that's important because I had a misconception there. I thought that the period doubling in something like Chris Monroe's experiment was essential. And what you're saying is that it's more or less
the signature of the phase. Is the signature of the phase, but I'm sure MD masters can come up with something that 3 of them are coupled, or so 4 of them are coupled, or something.
Oh, sure. Yeah. I mean, whether it's doubling or tripling, I don't think that matters. But if the system responded at the driving frequency,
there's more mode locking. There's mode locking, yeah, and those papers really establish mode locking very nicely. That's fine, but I'm trying to say it's only one of the criteria, because you could be fine-tuned to certain eigenstates of the problem which show mode locking. Yeah, establishing a phase, you got to really, if that's meant to be MBL is all eigenstates should show the same physics. And if you want phase, you have to show other criteria.
Okay, so let me ask one final question, which I think is more fundamental. Part of the idea here is that you want the system to be isolated.
Yes.
But you're driving it. So how does that fit into the criteria?
Okay, if you're asking, yes. Is in the definition. We are driving it in an isolated. What we mean is that it does not constantly absorb energy from the drive, and no new entropy is generated. If you convince yourself you're okay with this definition, this is all into definition. What we're demanding is no new entropy is generated.
Okay.
Such as, here's the historical root of it. When we decided that we got to move away, where we are forced to move away from equilibrium, we try to bring as many good features of equilibrium physics with ourselves because we want to define phases and whatnot. The thing that we put in our toolbox to bring was this: in equilibrium, there's no new entropies generated, and there's no net flow of energy between your system and environment. So these are the things that we are bringing with ourselves to define a non-equilibrium phases. These are the things that we bring with ourselves. And that's, if you just accept a driven system can be isolated so long as it is, I don't know, it's not intuitive, but if it doesn't absorb energy, then
it's sort of isolated.
These are kind of, maybe isolated is not the proper.
Okay. Anyway, I should let somebody else ask questions.
Pedram, this is Shankar Desharma. I had a couple of questions.
Sure.
So Bill, quick answer to your question is that what he means by isolated is no dissipation. Dissipation in either direction. Dissipation in either direction. So I have two questions. First one, both are kind of like perplexed me. I understood everything you said. So my question is not on any technical aspect of your work or questioning any aspect of your work. I understand everything is fine. And I accept everything you said, okay? But first question is, why did you choose this problem? Is it because the name time crystal will attract a lot of attention? Why not study MBL itself, which, as you repeatedly emphasized, is the main physics here? Why not MBL? Why all this drive? Why all this kabuki? Why not just study MBL in this model? I mean, I am really perplexed.
What I'm not we can.
Okay, all right. I think I got the answer from your reaction. Okay, so let's not go on. Okay.
But let me say one sentence. Maybe is there is all of these experiments. What we usually don't communicate publicly is lots of experimental tools have to develop in the lab. All of them look like an exercise to me, which stretch our capabilities, which we don't discuss what we have to develop in the lab. MBL would be, as soon as it's challenging, I accept it and the team would work on it. Yeah, sure.
Yeah, because in MBL, there are still some very fundamental questions we don't know the answer to. For example, is there a many-body mobility edge? What happens in 2 dimensions? I can give you a whole list, and I'm sure you know.
But those are too hard for me.
I agree. But I want answers to hard questions, which will be now my second question.
Yeah, probably our platform. I mean, you see how we stretch and argue and mixture of argue and experiment. We try to establish something. Those questions probably way harder for us.
My second question now connects with what you said. Those questions are very hard. What I'm perplexed about, and please take this question in the spirit I'm giving it, okay? Because I'm really perplexed. You have 20 qubits, your system size is in space 20, and your system size in time is 100, okay? I, sitting where I'm sitting, can do 22 and thousands of time steps, millions. Okay, I cannot do it. I have to ask the postdoc to do it on the cloud, but I know I can do it. Exact diagonalization. No, let me finish. Exact diagonalization. If I do excited set DMRG, I can do up to 40. Okay.
No, there's nothing unsolved in 1D.
So my question now is, why should I be impressed that you have done it with 20 qubits for 100 time steps? I mean, Bela Bauer in the original paper did 22 and long time step. I mean, I understand it has attracted a lot of press and so on, but I'm genuinely perplexed. What's new here? Why should I be impressed? Is it that you have done it? Let me finish. Is it that you have done it with actual digital qubits? I mean, which is very impressive. Is that the point here?
No. I tell you what's the point here. No, there is nothing in. Believe me, we are at Google. We do have access to very good computers, and we can do any problem with 1D. There is nothing we have. We have no illumination or nothing illuminative to say for people who do numerical simulation. This is an experimental work, and we try to guide the NISQ hardware teams how to study phases of matter with these systems. This is a hardware NISQ challenge. Your system is not infinite. Your time is finite. You have all these issues. How would you study interesting NISQ questions with your broken hardware? We are trying to communicate that with an experimentalist teams. That's the purpose of this work.
Okay.
How do you face a definition of infinite oscillation in isolation? How would you do it with your open system of 20 qubits? We're trying to guide the community in that way.
Okay. So the fact that others may have been able to do it analog simulation with larger system is not the issue. Issue here is that you are doing it with actual qubits. And the engineering fit is very impressive. I completely accept it. I mean, I have no qualms with it, that the fact that you can do it in the lab, controlling just very impressive. And maybe there is a NISQ community which is impressed by it. But as far as fundamental physics goes, I hope you and I agree that it hasn't added anything, in spite of all the press releases and press getting very excited. I mean, because when the thing came, I got very excited. I started looking at it, and then I sent an email to everybody. But the system size, is there hope that you can go to 100 someday? Because that will be something I can never do. Okay, and you may be able to do it one day.
Yeah. I mean, we could go. Well, yeah, we do have bigger chips in the lab, but the language that we wrote this work is about. Look, condensed matter physicists have been fascinated with phases of matter, and now we try to introduce NISQ as a viable platform to do physics. And we're trying to highlight the challenges and how to overcome these challenges. For instance, this finite size scaling we did has happened for the first time. So we're trying to show how these things can be done and talk to our experimental colleagues. And the definition I wrote first was very brief, infinite oscillation in isolation. And now I'm spelling it out. We're trying to explain this physics and how to do it one by one.
Okay, so
and then sometimes you can take it to the limit that maybe has some news for people like you. At the moment, it's a very experimental work.
Yeah, I think I understand what you're saying and accept it. What you are doing is developing a new experimental field, which is, you are calling it NISQ. I don't like that word at all. That's like snatching defeat from the jaws of victory, when nothing is, call it. But I like the idea of doing this new kind of experiment where you are doing it in a new lab with qubits, rather than, with atoms and ions. And you are developing the language and the tool of that experimental field. If that's what you tell me, I accept it. Then I accept it, okay?
Sean, let me ask you a question. What should we call NISQ? You give us a suggestion. This term is going to stick with us. The other term, supremacy, really bothers us.
I don't underestimate the importance of terminology. I don't need funding anymore in my life. So I do not use any sexy terminology just to attract attention to my work. But I think that what you are doing, both with the random circuit and this, are extremely praiseworthy. Although I didn't learn anything, but that doesn't mean I will not learn something from some experiment you'll do next year. Because on the cloud, I will not be able to go more than, maybe 26 qubits in next 10 years, okay? But you may be able to go to 100 qubits and show something in MBL or some other property that we theorists do not know. So it's a very worthy avenue for new research.
I mean, of course, our destination is to do something beyond capability of classical computers that attract the attention of condensed matter community. But this work particularly is not in that direction.
Can you do this experiment in 2 dimensions? This or MBL experiment?
Well, MBL in 2 dimensions probably not going to survive. But yeah, of course we can do the experiment.
Right? This probably, what you said is probably, and I accept exactly, but it's not definitively established. As you know, Emmanuel Bloch has some paper where he sees some, I also think that MBL doesn't survive in 2D, but this is just what I think. I cannot show it because simulations are impossible, If you can do even like 36 qubits, 6 by 6.
We do have, well, but this timing is not that. understanding you guys give me benefit of the doubt to accept these things as infinite time. So again, we ran into these problems very quickly. Did you watch it enough? Yeah, I mean, right. We are suffering from these problems, and we're trying to be very cautious.
Right. We theorists are limited by the linear size, and you experimenters are limited by the temporal size. We are not limited by the temporal size because we can just keep on running the computer for a very long time.
Right, and that's why the trick we played in the beyond classical experiment, which we get something which was really entanglement was growing very fast.
Right.
So quickly we could make a very complex state. But MBL means growth of entanglement and growth of complexity. Consequently, is a slower. So then matrix product states and other thing can catch up. So you have to be faster than something. So we are constantly fine-tuning and battling these things.